Hello guys, you're welcome back to our class again today. In this particular experiment, we are going to be determining the specific heat capacity of a metal block using the mixture method. To achieve our aim, here we have a metal block which we are going to deduce its specific heat capacity with a string attached, which we are going to use in inserting it into the calorimeter. And then we have our calorimeter here. Here is the copper calorimeter, and then the container well lagged. We have a thermometer, we have a beaker and a measuring cylinder. We have a chemical beam balance to help us measure the mass of water, and then the retro stand in order to insert the thermometer. We also have a heating source in order to heat up this particular metal block, and then the timer, because we're going to time the heating. So all of this represents the apparatus for this particular experiment. So using this apparatus, we're now going to go further into the procedure. I believe you can see the procedure on the screen at the moment. Now, the first thing we are expected to do is to measure a volume of 50 cm cube of cold water into the calorimeter. But before doing that, it will be important that we measure the mass of the calorimeter, because we are required to measure the mass of the water we are going to pour in. So if we measure the mass of the calorimeter and then pour in the water, we can find the difference, which will give us eventually the mass of the water. So let us find out the mass of the calorimeter empty. So I've on the beam balance. You can see it's at 0. So I drop here, and then we have our reading as 39.04 grams. As you're seeing here, 39.04 grams is the mass of this calorimeter empty. All right, now we were told to measure out 50 cm cube. So here is a measuring cylinder, and we have measured out a 50 cm cube quantity of water. Here you see, here we have 50 ml. You know that 1 ml is equivalent to 1 cm cube. So 50 ml will represent 50 cm cube. So this is the volume of water we have at the moment, 50 cm cube of water. And we are asked to pour this into the calorimeter. So remember that we have noted our value, the mass of the calorimeter, already as 39.04. So we are now going to turn in this 50 cm cube of water into the calorimeter. So having poured in the water into the calorimeter, let us now confirm what will be the total mass of both. So putting it on the beam balance, we have 88.61. Now that we have 88.61, all we need to do to get the mass of water would be to just subtract this value from the initial value of the calorimeter, and that will give us 49.57 grams. You can see that there is a little bit of a discrepancy in value, because sometimes the calibrations here are not actually accurate. We are expected to actually get 50 grams, but what we are getting is 49.57. So this is the most accurate method to actually find the mass of the water. So I have my mass of water here as 49.57 grams. So now we are going to find out the initial temperature of this water by measuring using a thermometer. You can see I have my thermometer here. So let us find out what will be the initial temperature of this particular water that we have. So I have the thermometer inserted into the calorimeter, and here I have the so we have the temperature to be about 26. Here is 26 degrees Celsius. So here is 26 degrees Celsius is the reading on the thermometer. You can see here, yes, 26 degrees Celsius. That's the initial temperature of the water, 26 degrees. Okay, it's falling, you can see. Let's just wait a bit to see whether it would fall to maybe 25. It's actually falling. You can see it's now at 25.5. You can see. So just a little bit of time, like 30 seconds more. Let's see what will happen. If you remain steady, then we can proceed. Now you have to be a little bit patient in this experiment because of these particular readings. It can actually affect your result. So let's see, what do we have? Okay, all right. So you can see what we have now. What we have now is just about 25 degrees Celsius. You can see it there, just 25 degrees Celsius. So we're going to use this value, 25 degrees Celsius, as our initial temperature of water. Now, I'll record this. Now, on the other hand, we have our heating source prepared and ready. We are going to quickly heat up the water here. So here, I have enough sufficient water to cover okay, let me reduce it a bit. Okay, so it will boil faster. So wait for this water to boil. Once this water boils, we'll insert this bowl and then allow it to boil for 2 more minutes, and then we will now transfer it gently and quickly into the calorimeter and stir so that we can find the final temperature. So let us wait for the water to boil. All right, so here is the boiling water, as you can see here. So we are going to simply quickly insert this, and then once we have done this, we'll start our timer and leave it for 2 minutes and see. The reason for leaving it for 2 minutes is to ensure that the metal has absorbed enough heat energy. So you can also confirm that the metal is directly inside the liquid which is boiling. So our time is at the 19-20 seconds point. So we'll do this for just 2 minutes, and then so here is what we have. So let's catch up. This is almost 2 minutes. You can see here is 1 minute 49 53. Are you set? 57, 58, 59, 2 minutes. So this is 2 minutes. Quickly transferred to them and then cover up. Let's watch and see what the temperature will be like, whether it is increasing. So here's what we have. As you are doing your stirring gently, be stirring gently, be stirring gently. You can see that there is a considerable increase in temperature. Be stirring gently. At the moment it's at 29. Be stirring so that it will be uniform. So we are stirring. So this is the final temperature. That's the 29 degrees Celsius. You can see it is uniform and steady at the moment. So we'll record the temperature as final as at 29 degrees Celsius. Okay guys, we are going to repeat this experiment for other volumes. Now we are going to proceed to volume 60 cm cube, and we'll repeat the same procedure. So we are going to remember that our calorimeter has a constant value of 39.04. We had already mentioned that earlier. And then in this case, we are going to be using a volume of water that is about 60 cm cube. Here is 60 cm cube measured from the calorimeter. Oh, sorry, from the measuring cylinder. So we are going to turn in this into the calorimeter and measure the new mass. So this is what we have. Ensure that you turn in everything inside the measuring cylinder. Now we have done that. Let us see so this is 98.50 grams. That is the mass of calorimeter plus water for 60 cm cube. So if we try to find the difference, it's going to give us 59.46, which is the difference. So the mass of water for this particular experiment is 59.46. So we are going to still find out whether there is a change. Maybe the room temperature has increased, so we're also going to find out the initial temperature of what it is expected actually to be the same, but for many reasons we'll just have to measure it again to be so sure that by virtue of heating this, the room temperature must have been affected in a way. So let's see whether it has an effect on the water that we are using. Recall that initially we got our initial temperature to be at the 25 degrees Celsius. So let us see what we would have at the moment. So here you can see that the temperature is about 26. Let's just give it about 30 seconds and see whether it will come down. You can see it's still coming down. There's a small reduction in value. Let's see. So whether we would have the same thing. So here is the initial temperature. So this is the initial temperature of the water for 60 cm cube. You can see it's just at 26 degrees Celsius. It is not actually coming down from that particular position. So at 26 degrees Celsius, we are going to actually just record this value, and then you can see exactly that it is at 26 degrees Celsius. Here is it. So we are going to now insert, we also have our boiling water with the mass, with the block already inserted. We are going to quickly transfer this and then find out the increment in temperature. Alright, so this is what we have. We're going to off this and then quickly transfer this to, so here we have, so let's see what will happen to the temperature, whether it will increase. So we have this, you can see 27 already. More mass of water inside, so let's see the effect it will have. Will the temperature increase or will it reduce? 28.5 at the moment. So let's see what will happen. $28.5, it has been steady at 28.5. Remember that the mass of the water in it is more now. So here is the final steady temperature, and it's at 28.5. This is been more clear. It's at the final steady temperature I have here reading at eye level is at 28.5. So I'm going to quickly record this as the final steady temperature, and then from there we'll proceed to the next stage. All right, so we'll be repeating this for the next time. That is using a volume of 70. I've already measured in 70 cm cube here. Let us find the mass. Remember, the mass of our calorimeter is constant at 39.04. Let us find the mass of the calorimeter and water. I have here 107.90. So with this, I can be able to deduce my mass of water. Now, I'm also quickly going to be finding the initial temperature of the water by inserting this and then finding the initial temperature of water. Let's see what we have for the initial temperature of water. So the initial temperature, as we can see here, is at 26 still. So we'll record the initial temperature for 70 cm cube at 26, and then our water is just about boiling. And then once that is done, we'll transfer. Let me increase the heat a bit so that we'll get that done fast. Okay, so here is our time. We are almost at the 2-minute mark, so we have this 59 and 2. So our time is off. I'll quickly transfer this to and close it quickly, and then we can now commence the so let's see what happens at this point. we'll see this at 29. Let's see, we'll leave this for some time and study whether it is steady. Okay, I see it's coming down. So this is what we have. As you're stirring, the heat is being transferred to every portion of the liquid. So the temperature is expected to go down when it becomes uniform. So let's see what we have. At the moment we're approaching the 28 cm, degrees Celsius mark. Alright, you can see that we're almost there, 28 degrees Celsius. Let's wait for about 10 seconds more and see what will happen, whether it will remain there. So I'm trying to stir this, and at the moment it is fixed at that 28 degrees Celsius mark to make it erect. Okay, so this is what you have. 28 degrees Celsius on the dot. So let us record this value, and then we have 2 more stages to go, and then we'll take it up from there. So we proceed further. This is already measured out 80 cm cube water, and then we want to find out the mass of this water. Already we know the mass of the calorimeter, so the total mass has given us 118.31 grams. 118.31 grams. And then we're going to find the difference in order to be able to record the mass of the water. So having done that, we are now going to find out the initial temperature of the water. So here I have my thermometer inserted. So let us find out what will be the initial temperature of the water. At eye level, if we measure at eye level, what we are getting at the moment is 26.5. 26.5. You can see it's just at the center point here, 26.5. So I'm going to record this as the initial temperature reading of the water that we used, and then we are going to we're already timing this, and it's boiling already. We will soon approach the 2-minute mark. So quickly we are going to get set for inserting the mass. All right, guys. So we can see our time is up. So I'm going to quickly transfer this into the calorimeter quickly and then cover it up. Let us see what is going to happen here. So I have the time here already at 29.5, you can imagine. So let us stir and see what will happen. I know that you know already that it's going to come down, don't you? So let us see. Already it's at 29 now. You can see as I'm stirring, it is coming down. Our expectation really is just going to be somewhere around 28. So let's see whether we will get our expectation, because the mass of the water has increased, and therefore we expect that the drop in temperature will either be the same or even more reduced. So let us see what happens. At the moment we are approaching 28. We are not there yet, but we'll soon be there from the look of things. So I have 28 point something. Just a few more minutes, and then we'll find out whether it has been steady. All right, so this is 30 seconds later. We have it still at 28.5. So that is actually what it has been. It has been steady at this point. So we'll record that to be 28.5. So this is the reading for 80 cm3. Final temperature 28.5. So we have just one more left, which is the 90 cm3, and then we'll proceed. Guys, this is the last setup. So we already know the procedure, so we just go straight to get our values. What we have here is 128.10 gram. 128.10 gram. From here, our mass of water will be deduced. All right, so if we point that, it will give us 89.06, and then that is for the mass of the water, 89.06 gram. So we will find out what will be the initial temperature of the water we are using. Here we have 26.5 at the moment. Yes, 26.5. So our temperature is 26.5. So let us record that, because I'm not sure it will go below this value. Okay. All right, so let's just proceed. This is 26.5 as initial temperature. So we'll now, the water is already, we've started our timer, we'll check, and then we'll insert the mass quickly. All right, our 2 minutes is up. We're going to transfer this quickly into the calorimeter. I believe that you're set. So let's transfer it quickly into and close, and then watch what happens to the temperature. So we'll also stir. At the moment we are at 27.5. I hope it will be able to rise further. This is 90 cm3, so you would expect that the mass of the water would affect the temperature or the temperature coefficient. So let's see what will happen quickly. At the moment it's at 28.5. So this is what we have. For the past 30 seconds to 1 minute, it has been steady at 28 degrees Celsius. So this is what we have at the moment. So I believe that this is likely the final steady temperature. So we are going to record this as our theta F, and then being the last procedure, we are going to now tabulate our readings and follow the other instructions that are there. We are going to state the precautions that we took while conducting the experiment, and then we are going to plot a graph. So just stay tuned as we compile our table, come back and analyze what we have at the moment. Computed all our values on the table. We need to measure the mass of the block. So here we have our beam balance at 0. So let us see what the mass of the block would be, because we will need it for a calculation in the question, the sample question we are using. So the mass of the block we use is 29.76 gram. Now we are going to quickly interpret all our values and then use it to deduce the slope. From there, the short answer questions that we have, will now answer them. Okay guys, this is the representation of our table from the experiment that we've conducted. On top of the table here, we have the mass of the block that we used, which was measured to be 29.76 grams. Now, aside that, we have the complete table, the composite table here with the volume, which we measured in the experiment 50, 60, 70, 80, and 90, recorded in cm3. The mass of the water as measured to be equal to what we have on that column. Remember, I showed you how we deduce this mass of water. And then the initial temperature of the water during the course of the experiment. You can see here that the initial temperature of the water is not the same all through. Reason being that one, we were using a heater that heated up the environment. So you expect that during the course of the experiment that the room temperature is going to increase. Thereby, that will also in turn affect the temperature, initial temperature of water that we use. So you can see that there's a gradual increase in the initial temperature of water used during the experiment. So don't always assume that it will always be the same value throughout the experiment. So I had to record based on what I got and measured in the conduct of this particular experiment. And of course, the final temperature which we also got was recorded there in degrees Celsius. Then we were asked to deduce the following: final temperature minus initial temperature, which is there next, 100 minus final temperature, which is also following next, and then we were asked to find R, which is equal to 100 minus final temperature divided by final temperature minus initial temperature. All this makes up our composite table, and we recorded them in the appropriate decimal places. So with this, we are asked to plot a graph of R as the ordinate and the mass of water as the abscissa, that is horizontal and vertical both. So this is what our graph represents. You can see that we plotted a graph of R against mass of water. On the vertical axis here, we have our axis distinguished R and mass of water on the horizontal axis. You see that our graph is a straight line graph, and then with that, we will now deduce our slope, and our slope gave us 0.7273 per gram. Now, from the graph, they asked us to deduce the value of CB, and they gave us a formula. S is equal to 4.2 divided by MBCB. Remember, now we're going to use the MB that we measured earlier, which is 29.76. That's the mass of the block. Substitute our slope, substitute the MB, and then make CB the subject formula. This is purely mathematical. So by the time you substituted that, you will get the CB to be equal to 0.194 joules per gram per Kelvin. Now, this is actually close to the specific heat capacity of a particular substance. So on comparison, I deduced that this value is actually approximately the value of the specific heat capacity of tin. Now, the specific heat capacity of tin is 0.2 or 0.21. So by approximating the value, you can see that the value we have is close to that. Of course, from the experiment, you will notice, and you can actually deduce that some experimental errors could lead to the deviation in the value. But this is pretty much close to the value of the specific heat capacity of tin. And of course, the material I used is actually made of tin. Now, going forward, we are asked to use the graph to deduce the value of the final temperature when the mass of water is 55 grams. Now, of course, you know that during the question, they asked us to deduce R, which is equal to 100 minus final temperature over final temperature minus theta I, that's initial temperature. So if I use that formula where we traced from the graph, we trace from mass of water to be 55 and then trace it to the R axis, we got that R is equal to 20. So we have gotten this value from the graph. Then, now that we've deduced our R to be 20, mass of water is given as 55 already, and then we're making theta F, or the final temperature, the subject formula. Substituting adequately into this equation, we got that final temperature is equal to 28.57 degrees Celsius. Of course, you can see the substitution is just simply a mathematical process. Substitute this. Our initial temperature, we used it at 25. That is theta I. And then by the time we expanded and made theta F the subject formula, we got it to be 28.57. Go back to the table to check. You could see that when the mass of water between 49.57 and 59.56, where the mass of water they give us as 55 lies. If you check the final temperature, theta F axis, if you check the column there, you will see that the value we also got was actually between 29 and 28.5. So that tells you that that deduction or calculation is pretty much accurate. So going forward now, we are asked to state precautions that we took while conducting this experiment. Number one, we avoided parallax error in reading the thermometer. Of course, you know that is accurate. We also ensured that the calorimeter was well lagged to prevent heat loss to the surrounding. This is one of the major precautions you would take when conducting an experiment on heat. Now, you will gently have to stir the water to avoid spilling, and then transfer the metal block quickly into the calorimeter to avoid heat loss to the environment. Of course, this is where some people will have challenge. Of course, you notice that the transference sometimes may be a little bit difficult, but you have to try your best to ensure that you minimize heat loss to the surrounding. Okay, now as we begin to wrap up, what is the statement that the specific heat capacity of copper is 385 joules per kilogram per Kelvin? Now, the statement states that, or the statement means that 385 joules of heat energy is required to raise the temperature of 1 kilogram of copper by 1 Kelvin. Now, finally, we have a question here. They asked us to calculate the thermal energy required by the bulb, because in the question they told us that a copper ball of 25 degrees Celsius is placed in a vessel of water boiling at 100 degrees Celsius until thermal equilibrium is attained. If the mass of the ball is 500 grams, calculate the thermal energy received by the ball. This is pretty much straightforward. They said the specific heat capacity of copper is already given to us as a hint there. So from the question, we got the initial temperature as 25, we got the final temperature as 100, and then the mass of the block given is 500 grams, which is equivalent to 0.5 kg. They're asking us for the quantity of heat required, that's the thermal energy Q, and then the C, which is the specific heat capacity, was also given. Using the straightforward formula Q, quantity of heat is equal to the mass times specific heat capacity times change in temperature. Substitute your values, you will get 14,437.5 joules. So this is what we have as a solution, and this is pretty much everything that we were asked during that this particular experiment. You could see that it is actually a very straightforward question, although the conduct may be a little bit very much interesting, as you have to be very careful to get the accurate result. So I encourage you to try yours, and I would like to get feedback from you as to how it went. Thank you for staying through with us. Please do well to subscribe to our channel, like and share, and turn on the notification buttons to get alerts from us. God bless you for staying through. Be blessed.